Hello everyone, and welcome to, in fact, the third month of the SCI Fine Chemicals Group and Young Chemist Panel's webinar series, and in fact the 10th webinar that we've had in that time, so quite an exciting time for us. I'm joined by two other helpers on this webinar, so I'm here as the chairman, Fred Hancock. I'm with the Fine Chemicals Group, and I have Oliver and Nessa from the Young Chemist panel. We're aiming to carry on the themes that we usually run through the summer when we have our conferences. These obviously are in abeyance at the moment, but we want to keep providing a forum for ideas in our major themes of R&D, in process chemistry, medicinal chemistry, synthesis, technology, all those areas where time moves on and things change, and we want to keep people up to date as much as we can with these areas. So I need to just make some quick statements about the webinar itself. We will have a Q&A after the first speaker, and then the second speaker will come in and we'll have a Q&A for the second speaker at the total end of the webinar. And you can put questions forward anytime through the question box, and please question as much as you like. I have to thank our sponsors now. We have a growing band of sponsors. We do appreciate their backing for our work on these webinars. So AstraZeneca, GSK, UCB, and IKA have all been able to sponsor us, and we are very pleased with that. And we're very thankful to the attendees who come every week. We have a whole range of regular attendees, and we get global attendees. So I could say afternoon in the UK, in Europe, but in fact it could be early morning or late evening for some of our attendees today. So, and we appreciate everyone who joins in and listens to us. So the first speaker is Iustina Slabu from Johnson Matthey in Cambridge. She graduated from the University of Salford and then went to work for Nick Turner for a PhD in the MIB in Manchester, working on biolytic cascades. And in September of 17, she joined Johnson Matthey in Cambridge as a biochemist, working in a biotechnology group. And her title of her talk is Modern Approaches to Reduction Reactions. So I'll hand over to Iustina.
Hello. Yeah, thank you very much for allowing me to present this very exciting project and research that we have done here in JM. So yes, I'm going to tell you a little about our bio-catalyzed nitro reduction processes. A very short introduction to JM. We are a global and sustainable business with a history that's more than 200 years old, and we work with customers and partners from across markets, varying from pharmaceutical and medical to automotive, industrial, and chemical production. We are mainly working in JM LSD. We are working with on catalysis projects for fine chemicals and API synthesis. We have a very varied portfolio of heterogeneous and homogeneous chemical catalysts, but also biocatalysis. And our very extended range of catalysts cover a variety of industrially important reactions such as cross-coupling, cross-coupling, asymmetric synthesis, ester hydrolysis, and nitroaromatic reductions. We consider ourselves to be technology agnostic, So we are not really biased towards one catalyst, but we always try to choose the best catalyst that meets that is more efficient and it meets the customer needs. So for example, if we have a heterogeneous catalyst and a biocatalyst that perform the same reaction, we would always go for the one that is preferred for this specific transformation. So this feature we applied in a project that we undertook. We collaborated with our industrial partner Amgen. We were interested in the bio-catalytic nitro reduction of a series of nitro aromatic compounds. Generally, the catalysis for nitro reduction, it is one of the most significant chemical transformations in the fine chemicals and pharmaceutical industries, mainly because the amine moiety is one of the most common in APIs, and it mirrors the considerable demand for new and improved synthetic methods to access it. Nitro reduction is a very robust industrial process, and it's mainly done using heterogeneous catalysis, a process that has been developed for multi-kilogram or ton scale. Homogeneous catalyses are not very often employed in commercial nitro reductions. However, biocatalysis still falls behind this well-established processes. Some of the main drawbacks of chemocatalysis in these nitro reduction reactions are mainly linked to functional group that are prone to reduction, that are present on the rings, to the use of expensive ligands, and also to the use of specialized hydrogenation reactors to perform this reaction. So we looked at this transformation from 2 points of view: catalysis, chemocatalysis, and biocatalysis. Generally, chemocatalysis for nitro reduction uses various metal sources. A few of them are shown here. Palladium is the most versatile metal for reductions in general. Platinum and nickel are also used. However, they all come with strength and weaknesses, because palladium can struggle a lot with aromatic nitro reductions, and in this case, platinum and nickel are preferred, although nickel is usually more difficult to handle. From a biocatalytic perspective, the nitro reduction could be performed using a nitro reductase coupled with cofactor regenerating system. However, this process needs to overcome a very important difficulty, and this is the fact that it stops to the hydroxylamine intermediate, and it doesn't want to progress to the final aniline. And this is due to the general mechanism of the nitro reduction reaction, which is a complex reaction, and it results in quite a complicated reaction mixture, because in the typical head-cut nitro reduction, we have a fast reduction of the nitro group to the nitroso, followed by a fast reduction to the hydroxylamine group, and the hydroxylamine very slowly converts to the corresponding aniline, and all these intermediates, they would give rise to some dimers, to the azoxy, azo, and hydrazo intermediates. So it's quite a complicated system, and it's difficult to access the final aniline. So we decided to look at nitro reductases. They are not new enzymes. They are known to be FM-independent enzymes. They are known to reduce a large range of nitroaromatic compounds. And they have various roles in product activation, in bioremediation, detoxification, or oxidative stress regulation processes. However, as I mentioned before, the activity is limited to the formation of hydroxylamines, and the corresponding anilines are very rarely accessed. They are So we have used the type 1 nitro reductases. They are oxygen insensitive, and they reduce the aromatic nitro compounds through a series of 2 electron steps via a ping-pong mechanism. The first step, which is the slow one, is reduction of the nitro group to the nitroso, followed by a very fast step reducing the nitroso group to the hydroxylamine. However, the aniline, as I said before, very rarely access to this method. Although in the literature, there are reports suggesting that some very specific substrates are able to be reduced all the way to the corresponding anilines. For example, TNT, on TNT usually 1, sometimes 2 of the nitro groups are reduced, but the reduction of all 3 groups is very rarely performed. Nitrofurazone, and then some prodrugs that are activated very easily using nitro reductases. So, as I said, we started looking at reducing this nitropyridine in a project we carried on in collaboration with Amgen. And what we did first is we had a look at our enzyme collection, our nitro reductases. We screened all of them, and when we looked at the results, we noticed that most these are just selected results, so for a limited number of 4 enzymes, we noticed that all the final reaction mixtures contained the hydroxylamine. Some anilines were also made, but never more than 10%. And we could also see from the intermediates, mainly the azoxy was made in about 10% amount as well. So we decided to have a look and see what HEDCAT does and how they deal with this nitro reduction. And we learned that the aniline is generated by a slow disproportionation of the hydroxylamine. We also learned about catalyst modifiers, so these compounds that can modify the catalytic effect and rate depending on their concentration. And we also found out that the most common catalyst modifier is vanadium, which can be used either as an additive or it can be incorporated in the catalyst structure. We decided to take the first option, so we used vanadium as an additive, but we didn't stop at vanadium, and we tried to screen a large number of salts. We screened vanadium in 3 different oxidation states. We screened other metals used in this process, such as iron, cobalt, copper, and so on. We noticed that some metals have performed much better than others. However, vanadium was by far the best catalyst, the best promoter for this reaction, and especially vanadium in oxidation state 5. Although iron and copper have shown some promise, but the reaction rates were much slower, and they would allow the azoxy intermediate to accumulate because the hydroxylamine wouldn't disproportionate at a fast rate. We took these lessons and we looked again at the combination of enzyme and metal additive. So we have understood better the bio-catalyzed nitro reduction in collaboration with the metal, and we have seen that when vanadium was used, the aniline was generated via this metal catalyzed disproportionation. That also helped reducing greatly the accumulation of dimers. And it's also quite interesting to see that the reaction mechanism is very similar to the one that we saw earlier in the HEDCAT with aromatic nitro reduction. However, different steps are rate limiting. So in our case, the transformation of hydroxylamine to the aniline was very much accelerated by the use of vanadium. With these results in mind, we wanted to test the scope of this reaction, and we chose quite a variety of substrates that contained groups that are prone to reduction and any other side reactions, such as halogens, alkenes, some nitriles, and also some benzylated alcohols. So when we tested all these substrates in our reaction conditions, so at this point we are talking of a quite small scale. So the reactions were done on a 20 millimolar nitro substrate using 10 mg per ml catalyst and on a scale of 500 microliters. I have here a comparison between, on the left side you have the amount of aniline formed without the presence, without the vanadium, the promoter, and on the right side is the concentration of the conversion to anilines in presence of vanadium. So for the majority of the substrates, we have seen that the conversion to aniline has improved greatly. We got over 90% conversion for a lot of them. For some of them, depending on the combination substrate enzyme, we had very different results. So either very low conversion or quite high amounts of anilines. However, some substrates, such as this para-iodonitrobenzene and nitroisoquinoline, they seem to struggle quite a lot with all the enzymes, and the conversions to the final anilines were quite low. And we've also noticed that the metal didn't seem to have a high influence, so it didn't matter much if we added it or not to the reaction system. So we have observed that the bio-catalyzed nitro reduction is a versatile process, allowing a large number of substrates to be reduced and a number of metal salts to be used in the reaction. There is a certain degree of selectivity, and it allows the nitro-nitroso and azo groups to be reduced, while the other reducible functionalities are left intact, such as nitrile and the vinyl and the halogens. With the halogens, yeah, the most important feature, we've seen no loss of the halides, unlike the transition metal catalyzed hydrogenations. Then we wanted to see if we can push it a bit further. So we did reaction intensification with a 200 millimolar substrate concentration. We did a few preliminary studies, and we saw that the best way to go with this reaction is a fed batch addition. So we were adding the substrate at a 50 millimolar rate every hour. And after 6 hours, we noticed the complete conversion of the nitro substrate to the corresponding aniline, and also this was accompanied by a very very small amount of intermediates and side products formed. Further optimization work was carried out, and we managed to scale up this reaction to 70 grams per liter substrate and 2.5 grams per liter enzyme. Which is real progress compared to the small scale substrate screening that we've done before, with a conversion to the corresponding aniline of 90%. In conclusion, we managed to develop technology that has no precedence in the field. Although a combination of metal and enzyme is well known. We have also seen that the bio-catalyzed nitro reduction is selective and it is scalable. So we decided to start preparing a nitro reductase commercial kit, and we are also working on scaling up the reaction even further. And probably the most important message is the collaboration. It was a collaboration with the customers, so we had this very exciting opportunity to work on this project. It was the internal JM expertise in different catalysis technologies so that allowed us to find out-of-the-box synergistic solutions for this problem, and also our expertise in enzyme development because we can cover engineered enzymes, metagenomics, and rationally picked database enzymes. With this, yeah, I came to the end of my presentations. I would like to acknowledge all my colleagues who have worked on this exciting project from across JM, and also our collaborators from Amgen. And yeah, I would like to thank you for listening, and I would love to answer any questions you might have.
Cool. Yeah, that was a really exciting talk. So for those of you who would like to ask questions, can you please type those into the questions tab? And it would also be great if you could type in where you're dialing in from, and also the institution that you're affiliated with. I think we've got a couple coming in, but I'm going to jump in straight away with a question. So yeah, it was a really nice talk, Iustina. I'm just wondering about how you actually measure the rates of these reactions. Is it the same as normal reaction profiling? And then I suppose also what actually is the impact of the vanadium, I suppose, co-catalyst, and how does that impact the reaction mechanistically?
Yes, so the reaction rates are quite fast. For the substrate, for the nitropyridine that we've done most of the work on, and we used it as a model substrate, we saw that the reaction went to completion in 30 minutes, working on the 20-25 millimolar scale. For some other substrates, they needed a bit longer, so sometimes we had to leave the reactions overnight. Now, the role of vanadium is, yeah, it's one of the most important problems here, because what we probably don't understand it perfectly. So we know that it helps the disproportionation reaction, but we have seen that it really has to work like a synergistic collaboration between the enzyme and vanadium, because if we just throw in the enzyme and we form the hydroxylamine, and then we put the vanadium much later in the reaction, the conversions will not be that great. So they really have to work together. Everything has to be put in from the beginning of the reaction, and this allows the accumulation of the aniline and really drops down the concentration of the dimers and all these side products that we don't want in solution. I hope this answers the question.
So yeah, I guess so. So is it just acting like a Lewis acid, and that just catalyzes disproportionation of the hydroxide?
Yes, as far as we understand, yes.
Cool. Okay, I'll pass over to Nessa.
Sounds good. So we've got a question coming from Kong Chen Chuang, and they're asking, it's kind of a two-part question. Firstly, about the recyclability of the catalysts, and also about the workup. How do you obtain the product after you've run this reaction?
So if we talk about the enzyme recycling, we don't do this at the moment. We are planning to look into immobilizing the enzyme and also immobilizing the metal promoter, so we can run these reactions in flow. Yes, the second question, how we obtain the product, I think it was.
Yeah, about workup purifying.
Yes, it's really a simple workup of the reaction. So the reaction mixture usually is spun down, so you can remove all the enzyme debris, and then yes, and then the supernatant is worked up like a normal chemical reaction in which you have to extract an aniline. So it's quite an easy recovery of.
Yeah, that's good to know. That was kind of my question as well. Never worked with this sort of thing, so it's always good to know that it's easy to actually get your product out.
Okay, so we got a question from
Yes,
Holly Foster
yes,
from University of Leeds. Hi, Holly. So she says, have you ever investigated reusing the catalyst after isolating it?
No, as I said before, no, not yet. Because mainly we are working with very small amount of catalyst, so we basically have 2 mg per milligrams of gram of enzyme. However, as I said, we're planning to immobilize it on different supports and see how well we can recover it. One thing that's really good about the nitro reductases we worked with is that they are incredibly stable and active. So this helps a lot in immobilizing and using them in flow. But this is work in progress, so we are working on these things at the moment.
Cool.
Great. We've got a few questions from Richard Foran at GSK, who is one of our future speakers, if you want to tune in a couple of weeks. I kind of want to ask all these questions, but I'll pick one of these for now. He's asking, from your knowledge of the enzyme structure, how promiscuous would you expect these enzymes to be when they're working on more complex substrates, like maybe late stage pharma intermediates?
So yeah, what we refer to as promiscuous enzymes, yes, they can. Well, I would say they easily reduce the nitro group, but it depends a lot what groups you have on the ring, because if I'm not sure if you can still see my screen.
Yep.
Okay, so if we are looking at substrates like 2-ethyl nitrobenzene and this methylated nitrobenzene here, these are actually quite bad substrates. And sometimes it's related with the presence of the ethyl in autoposition from the nitro. However, depending on the functional groups on the ring, for example, if you have strong electron withdrawing groups and you have quite an extended pi system, then you have more chances for the reaction to work straight to the final aniline. So it's a matter of screening the enzymes, and we have a very, very large collection of enzymes, and also, you know, we can always do an engineering project and try to see how we can improve the activity.
Yeah, that's great. That's useful.
Should we ask another one of Richard Horan's questions?
Go for it. I reckon we've got time for like 2.
Yeah, there's good questions from Richard. So the second question he asks is it possible to stall or halt the reaction at the hydroxylamine intermediate? Because he then goes on to say that could be a particularly useful intermediate in other syntheses.
Yes. So what we have noticed is if we perform the reaction at the lower pH, at pH 6, and we don't add the method promoter, obviously, the reaction always stops at the hydroxylamine. Now, another problem is that that hydroxylamine can be quite active, and if it accumulates in a high concentration, it will disproportionate, so it will finally end up with a bit of aniline there. Also, you have to look at the enzyme preparation. At the moment, we are using cell-free lysate, so it's not a purified enzyme. It has some other things in there, so it is also possible that there are some trace metals in the enzyme composition that could promote the disproportionation. But generally speaking, what we have noticed is a pH 6 and no vanadium results in the formation of the hydroxylamine exclusively.
Okay, so in terms of the vanadium, is that, which step is that actually acting in? Is that disproportionation of the
it's
hydroxylamine, or is it the?
Yes, that's correct.
So it's not involved at all in splitting of the diazo species after that?
So we suspect, because we have noticed this, we've done some experiments, we suspect that the azoxy is also accepted by the enzyme and reduced to the diazo, and then the diazo is reduced to the hydrazo. And we have seen that the hydrazo compound is possible to be disproportionated by vanadium. So it goes it can form the aniline. We have seen this, we are postulating it, but obviously we need to look more into detail. What we know for sure is that vanadium is involved in the formation of the aniline from the hydroxylamine.
Yeah, that's a really cool mechanism, that. Nessa, do you want to go for one more and then we'll switch over to Stephen's talk?
Yes, let's do that. We may be able to answer more questions at the end of both talks for both speakers. But just before then, there's one coming in from Ankit Porde at the University of Nottingham, who is asking whether you've observed any inactivation of the enzyme by the metal additive during the timescale of the reaction.
Yes, that's actually very interesting. We have noticed, yes, certain metals, such as gold, for example, they completely inhibited the enzyme. So we saw absolutely no activity at all, not even to the hydroxylamine. However, we did run an engineering project, and we have noticed that some mutants also were inhibited by vanadium. And this is probably due to the fact that nitro reductases, they are very close to a class of chromate reductases. So they are able to bind and reduce the metal. And probably the binding is so much better, and it competes to the binding of our nitro and nitrosome substrates. So we did see inactivation, but at any point we had, you know, we had a large collection of enzymes, so we could always find another enzyme that's not inactivated.
Right, that's very nice. It's very interesting. All right, well, thank you very much. I think I'll pass over to Fred to introduce our next speaker.
Thank you.
Really nice talk, really good.
Yeah, it's a fantastic talk.
Thank you.
So our second speaker for this webinar is Stephen Thomas from the University of Edinburgh. Stephen did his MChem with Nick Tompkinson in Cardiff, and then moved to work for his PhD with Stuart Warren in Cambridge. And after that, he postdoced with Andreas Falz in Basel. So you can see he's going to end up in catalysis. And after a brief stop in Bristol, he was in 2012 he was awarded a Chancellor's Research Fellowship at the University of Edinburgh. And his title of his talk today is Main Group Catalysis for Hydroboration Reactions. So over to Stephen.
Thanks very much for inviting me to give this talk. Thanks very much to our previous speaker. I was a member of the YCP, the Young Chemist panel, so it's great for them to invite me back, and thanks to the Fine Chemical Group for doing likewise. So before I start, I would like to thank my group. I can make the slides go forward. Okay, so I don't do any of the work. These are the guys who do everything, and it couldn't happen without them. So I really am very thankful to them. Today I'm going to talk about three people's work mainly, and that is, Joanne and Kieran, and a little bit of Andrew's work. So quite different from earlier on, I want to talk about some main group catalysis, some very small molecules, and one specific reaction, which is the hydroboration reaction. And when we think about hydroboration reactions, we need to just get a couple of things straight, or I want to make sure that we've got a couple of things straight. Unlike boranes, boronic esters, or dioxyborolanes. So here's HP pin shown on the slide. They do not add across alkenes or alkynes by themselves under standard reaction conditions. What you need is a metal catalyst to do that. And in general, that metal catalyst is a precious metal, so something like rhodium or iridium, or first row transition metals are now coming to the fore. And when we think about how those reactions or how those metals do this reaction, we think about classical organometallic chemistry. We take a low oxidation state metal and we do an oxidative addition into the BH bond to generate a metal hydride and a metal boryl. So the metal goes from N to N+2, that oxidative addition step. We then add in the alkene or alkyne and a hydrometallation reaction, the addition of the H and the metal across the alkene in a syn fashion gives us this organometallic intermediate and makes our first bond, that CH bond. We then do a reductive elimination, which makes our boron carbon bond to give us the product and kicks out the metal in the original oxidation state. So we're in a 2-electron manifold going between N and N+2. Okay, so we got into this area by thinking about aluminium, and could we force aluminium to do this kind of chemistry? We wanted to move away from the D block and try and force that reactivity on the main group, on the P block. And so we were aware of or a number of aluminium-1 compounds. So here are 2 examples, one from Herbert Royski, sorry, on the right, where we've got this NAC-NAC anionic ligand, and then again the original CP-, these 2 aluminium-1 species. We're not particularly focused on low oxidation state main group species, so we called in an expert in Mike Cowley, one of my colleagues here at Edinburgh, and this is all done with him. So the idea is to take these aluminium-1 species, take that, do the oxidative addition to give us that alane and our aluminium boron bond, aluminium-1 to aluminium-3, hydroillumination, that's the hydrometallation step, to give us a carbon aluminium bond, and then reductive elimination, that will kick out, should be an aluminium-1, and make our boronic ester. So on paper it looked great. In reality it was rather more difficult than I'm presenting. But what we did notice, or what we thought about, was what's the real problem here, and it's that reductive elimination. The oxidative addition step is known for aluminium-1 type species, and various molecules have been used here. Hydroillumination, pretty well known. Reductive elimination for most of the main group is still quite rare, and so we really figured this was the problem step. So what we had to do was focus on the step that we knew we could do, and the easiest of those steps, and that's the hydroillumination step in my mind. As the introduction said, I'm an organic chemist, and so aluminium-3 is how I think of aluminium. Aluminium with a hydride on it, aluminium-3. I think about things like dibal and lithal, and we had a very good student at the time, Alex Bismuto, and he found that he could use very simple alanes to catalyze this aluminium catalyzed hydroboration reaction. And so if we take dibal or lithal, that will work, but we could also use this triethyl aluminium Dabco complex, which is effectively the ethyl analog of Simon Woodward's trimethyl Dabco, trimethyl aluminium Dabco complex, which you can buy from Aldrich. What the Dabco does is allow you to be able to weigh this out on the bench. It's no longer pyrophoric. So this acts as a surrogate for triethyl alane. And what we noticed in the reaction was that we could take the HP pin and our precursor to generate that alane if we're starting from something which is trialkyl, that would undergo the hydroillumination, and then this exchange process now, which is much more common for the P group, where ligands are rearranged based on stoichiometry. And it really is that step that caught our eye and has really kept us entertained for quite some time. And here what we're doing is swapping a carbon aluminium bond for a carbon boron bond. And in that process, that swaps this boron-hydrogen bond to regenerate our alane catalyst. So that hydrogen ends up on the aluminium and the carbon ends up on boron. It's a group 13 exchange reaction. There is a problem with this reaction, and that was that alkenes needed really high temperature to do this. We're talking 100 degrees in toluene, over 100 degrees in toluene to make alkenes work. So we realized there were some problems with the reaction. At the same time, John Carney was working on some manganese catalysis, and one of his project students who was supervising, who I haven't got a picture of sadly, Connie Bootner, did an amazing job of realizing that this reaction wasn't only metal catalyzed, that there was a background reaction here. And what the background reaction was that BH3 was being generated in the reaction. And once you generated BH3, that was catalyzing a hidden catalysis, if you like. So you'll notice here we're adding sodium tetrodoxide. That was to activate the manganese catalyst and effectively act as a reductant. But in this list here, sodium tetrodoxide will also react with H3 to generate BH3, and so there is a background reaction catalyzed by the borane. And really that's what I want to talk about today, borane catalyzed hydroboration. And we're not the first to have done this. Almost 30 years ago, periastomy showed that if you take diethyl aniline borane complex and HB-cat, an alkyne, you could catalyze the hydroboration of that alkyne to give you the catechol boronic ester product. That was followed by Hoshi and Arseni, who showed that if you take dicyclohexyl borane and HB-pin now, you could get to the pinnacle alkenyl boronic esters. And following on from the work we'd observed in terms of the aluminium and the manganese, we found that just simple borane complexes and in the presence of H3 would catalyze that reaction. And importantly, this would work for alkenes at much lower temperature. And so that really caught our attention. Why was the hydroboration faster than the hydroillumination, and what potential did this reaction have? So commercially available borane THF or 9BBN solution, H3, and we can do a boron catalyzed hydroboration. A rather simple reaction, but one we quite like. So to figure out if the mechanism we thought was working or how this reaction was working, we joined Guy Lloyd-Jones here, and he and Andrew figured out what was going on. So we take our borane and we do exactly as we did previously and bring in that alkyne to do the hydroboration reaction, syn hydroboration across the alkyne to give us this intermediate dialkyl, sorry, well, I guess it is dialkyl, alkenyl borane. Importantly, we've got all carbon around boron in this intermediate. When we bring in HB-pin, we noticed that you get exchange to the boronic ester and you get regeneration of the borane catalyst. And this step is exactly the same as that aluminium step, except where we're not changing an aluminium, we're changing a boron for another boron. So the blue boron, which is our all carbon substituted boron, is swapped with our H3 to give us the alkenyl boronic ester product, so 2 boron oxygen bonds, and a new boron carbon bond, and the hydrogen or the hydride from our H3 is then transferred to that borane to regenerate our catalyst. We termed that boron-boron exchange transborrelation because it looks a bit like transmetallation. If this was lithium and this was magnesium, that would be a transmetallation. And so here we're swapping the alkyl borane for the boronic ester. And some labeling studies with B10 HB-pin show that this reaction proceeds via the mechanism I've drawn here, a sigma bond metathesis type mechanism. What's important about this is that the entire blue boron group is transferred, as is the entire red boron group. And so you're getting complete transfer of both those groups. And so there is no breaking of any of the bonds around boron except for the BH and the BC. You can think of it, I guess, as a hydroboration of this bond. And that ties in nicely with the work of Fred Fontaine, Timo Ripo, Martin Strike, and Doug Stefan, where they have shown this boron-boron exchange for arene borrelation. So Fred, this is one of Fred's catalysts, has made these amino-borane catalysts, which will borylate heteroaromatics and turns those over with HP-pin. And it's the same transition state, an exchange of one boron for another through a 4-member transition state, a sigma bond metathesis. Okay, so at this point, it seems very inorganic to me. And we really asked ourselves, how can we exploit this exchange process, but in an asymmetric manner? And when I did my postdoc with Andreas, I swore I'd never do asymmetric catalysis again, but I guess enough time out of the game brings you back. So how do we make this process asymmetric? Well, we need an enantio pure, enantio enriched borane. We also need a prochiral substrate. And we're going to stack the game in our favor and use a ketone. A polarized bond helps us, and it also means that our stereochemistry will remote from our exchange process. That means we're going to get a borinic ester intermediate, so 1 boron oxygen, 2 boron carbon bonds. And when we bring in our HP-pin, our terminal reductant, so our turnover reagent, we'll exchange the alkyl borane for the boronic ester to generate a masked alcohol. So the product we'll get out of the reaction is formerly the alkoxy boronic ester, but of course when in workup that will become the alcohol. Importantly, the H from the HP-pin regenerates the borane catalyst, and so we can go in the cycle. And these are the simplest catalytic cycles I think we've ever worked with. It was certainly a lot easier on ChemDraw. Key to turning the whole thing over is that exchange process. We're going to break this BO bond with that BH bond of HP-pin to generate our product and regenerate our catalyst. So the catalyst is forming at the top and the product is forming at the bottom. Okay, I wouldn't be talking to you about it if it didn't work. So at this stage, Kieran and Joanne really have done a great job. I can't thank them enough, and I'll tell you about their work. So using acetophenone as our model substrate, we set about looking at how we could do this. And we took 2 very common boranes, or very easily available boranes, Corey, Cbs Reduction, and one of John Soderquist's, for want of a better word, chiral 9BBN. So this is a ring expanded version of 9BBN with the stereochemistry. And what we can see is 2 very different results here. 10% reduction, good EE. Very good reduction yield, poor EE. So that made us think about what was going on in this reaction. If we think about the Cbs reagent, what we're getting is very good reduction. It's a highly enantioselective process, which we would expect, but we're not getting any turnover. 10% catalyst is giving us 10% product. So we're not managing to get this transborrelation, this turnover, and HP-pin doesn't exchange with this, and that's why. If we look at the Soderquist reagent now, it's completely different. We're getting very terrible reduction. It's racemic, but we're getting lots of turnover. So we're managing to do the transborrelation and drive catalysis forward, regenerate our catalyst, but we're not getting any selectivity in the first step. And so we've kind of lucked out on both of these in the complete opposite way. But from a point of view is, would this reaction work? Can a BO bond be broken with a simple exchange process? Because thermodynamically, this doesn't look particularly favorable. The answer is yes. So we had to go back to the drawing board and think about how are we going to do this reaction and how are we going to get good selectivity. And we went back quite some time, 50 years ago. Mark Midland used alpine borane, now commercially available, for the reduction of propygylic ketones. And using this reagent, a Meerwein pond of Varley type reduction of this ketone gives you a borinic ester in high enantioselectivity. Now, this isn't a direct BH reduction, it's a beta hydride transfer. So we're transferring this hydride from the reagent in a concerted cyclic transition state to the ketone. So the hydride ends up at the carbon and the boron ends up at the oxygen to give us this borinic ester intermediate, exactly the intermediate we wanted. That kicks out pinene, so the beta hydride transfer generates the pinene there. And as you work up the reaction, you'll get your enantiomer-enriched alcohol product. And in that process, you destroy this 9BBN borane reagent. So essentially, you take a stoichiometric amount of alpine borane and you turn it into pinene, an alkane, and some boric acid. So what we wanted to do was turn that over. Can we intercept this intermediate and turn it back into the catalyst, and then we don't need to use a stoichiometric amount of alpine borane? And our thinking is that transborrelation will do it. Exactly what we're trying to do with those direct BH reductions, but can we use this beta hydride transfer to do it? Okay, so we began like good inorganic chemists and did stoichiometric single turnover reactions. If you take your ketone and alpine borane and mix those two together, you will generate your boranic ester intermediate, and that goes quantitatively. We're following this reaction by Boron Nmr. And we can see the trialkyl borane turn into the boranic ester. We add in HB-pin, that's to test our transborrelation, our turnover mechanism, and great news, it does turn over. We generate the alkoxy-boronic ester, and that shows this is going forward. We can check the EEs of both of those, and so the EE at the intermediate, the boranic ester, is the same as the boronic ester, the alcohol product, and so we're not losing any enantioselectivity in this exchange. The exchange is proceeding with retention of stereochemistry. I guess we'd expect that. It is remote from the stereocenter. But we need to look at this side of that reaction and look for the borane. And what we don't see is the regeneration of the alpine borane. In fact, all we see is 9BBN. And so we're doing the exchange, but the 9BBN is then building up and nothing is happening. We can see pinene and 9BBN as stoichiometric products of this reaction. So Andrew came along and said, well, Stephen, you've missed some fundamentals, which is generally the case. And presumably what's happening is you're freeing the 9BBN, but alpha pinene is too bulky, it's too sterically encumbered at the alkene to undergo a fast hydroboration reaction. So although all the steps work, it's the regeneration step that doesn't work, because now we have to do an alkene hydroboration to regenerate our catalyst. So why don't you just swap to beta pinene, which has a terminal 1,1 substituted alkene, and that should be faster than the internal alkene, and you should get reactivity. And actually, mertenyl borane has already been used for these type reactions, so it seemed like a viable pathway to go down. So if we take that isomeric borane, so we're using the term beta pinene now to give us this terminal, rather than the internal, for a better word, borane, we're still going to do a beta hydride transfer to give us that boranic ester. We're exactly the same product as above now. Again, this goes, we can see conversion of the trialkyl borane to the boranic ester. The EE of this is pretty good. When we add in our 9BBN, sorry, our HB-pin, we can see turnover, and so exchange of the alkyl borane for the boronic ester to give us this alkoxy boronic ester. And the EE again matches both of those two things in the intermediate. And then more importantly, we can see the generation of our catalyst again. And so we've managed to turn this whole reaction over, and we've managed to set up conditions to do this in a catalytic manner. And so let's do that. Let's take our instead of using stoichiometric, let's use 20 mol% mertenyl 9BBN, 120 mol% HB-pin, and see what we get. And we do get that alcohol in 80% EE. So I just want to focus on that a little bit. We're getting this transborrelation to turn us over. We're using a substoichiometric amount of our borane loading, and we're using HB-pin to drive the whole thing forward. So we've managed to make catalysis work with that 50-year-old reaction using a very simple P-block exchange reaction. We do have to extend the reaction time, and we do have to decrease the temperature to ensure high EE, but the EE isn't bad. And so under catalytic conditions, we get a pretty good yield and a pretty good EE of this product. Now, I don't want to spend a lot of time on EE. What I want to do is compare that EE to what you would get if you used a stoichiometric amount of your borane, because essentially that's the best you can ever get under catalytic conditions. So using a stoichiometric amount of borane, we get 81% EE. If we use 20 mol% borane, we get 80% EE. And what we're going to do is use this terminantio fidelity, where we basically divide one by the other and times by 100 to determine how good our catalytic regime is. Can we match the stoichiometric reaction? Because that's the only time this is a valid reason for doing this. So in this case, we get 99% EE. We basically match EF, sorry. We basically match the stoichiometric EE. Okay, so we'll do some substrates. I won't do methyl ethyl futyl. I'll just try and pick some highlights. We're going to make the catalyst in situ. We don't preform our mertanol BBN, mertanol 9-BBN. We just take H9-BBN solution and beta-pinene, mix those two together, and that gives us our catalyst. That's our benchmark, our simple phenol substituent. We can put some bulk on that, and that works well. The EF remains high. That's the key here. If we take a group you would normally expect to be reduced by a borane that survives the reaction, or the yield is slightly lower, but the EF is maintained. This is a workup problem more than anything. If we look at something which is really super reactive, a nitrile with stoichiometric borane is not being reduced at all, and we're getting very good EF for this catalytic reduction, catalytic Midland reduction. And we can go away from some functionality. You will notice they are all propagylic or nitrile derivatives, but that's enough of a handle for further reactivity. If you'd like to do some biologically type molecules here, we've got proferol, infamous for its role in Michael Jackson's death, which works very well, a good EF, and again, this highly substituted sugar derivative, which doesn't impede catalysis. We get good yielding, good DF. And the reaction, a diastereoselective reduction now. Of course, it doesn't work for everything. We get low yields with this CF3 substituted ketone, and that's because the background reaction is so fast between the reagents we're putting into the reaction. So the 9-BBN that we use to make our catalyst and the HB pin, which have a stoichiometric amount for turnover. So the way we get around that is just do a slow addition of HB pin, and that takes that EF up from 19% to 83%. So we're getting much more towards workable reactivity. The same thing can be done by increasing the steric bulk here. We get rather poor EF. That goes right up by decreasing the amount of H9-BBN and keeping an excess of pinene. That ensures we're always making catalysts, and so the EF goes up to match that. Okay, so I want to finish with the catalytic cycle. I'm conscious of time. How is this reaction working? It's a bit more complex than what I drew at the start. Well, we're going to take our pinene and our 9-BBN and generate our catalyst in situ. Once we have the catalyst, we can add in our ketone and do an enantioselective hydroboration to generate our boronic ester intermediate. That goes via that MPV Midland, the Midland reduction going by an MPV reduction, the beta hydride transfer to the ketone. That regenerates our pinene. When we add in our HB pin, we kick out the product. We do our exchange reaction between those two borons. The blue boron is swapped for the red boron, and we regenerate our 9-BBN under reaction conditions. Importantly, this is regenerated in the presence of alkene. The alkene comes out before the 9-BBN is regenerated. Transborrelation effectively locks the 9-BBN with the BO bond until the HB pin sees it. That releases our H9-BBN. It reacts with the alkene chemoselectively to regenerate the catalyst and go through the whole cycle. Importantly, we don't see any deactivation either by boron-boron exchange, transborrelation at this bond, or unselective background reaction by the H9-BBN or the B pin. And so we've managed to set up a cycle where the Midland reduction is giving us our EE and transborrelation is giving us our turnover. And because this controls the concentration of the H9-BBN, we only regenerate the catalyst in an excess of alkene, or an equivalent of alkene. Okay, perfect. So a rather more complex catalytic cycle, but one that works really well for us, and one in which the rates we've controlled perfectly to ensure high EE and EF, matching that stoichiometric reaction. All right, so in summary, I've started with some boron-catalyzed hydroboration, where we saw alkenes and alkynes going through this. I didn't talk about this diborrelation reaction that we published recently, And I finished with this unpublished work, which is on ChemArchive if you want to see it, where we're doing the asymmetric reduction of ketones using a catalytic Midland reduction. I'd like to thank the guys who did the work, particularly Joanne, Andrew, Kieran, Peter, who's not here, he's now at the RSC. These guys for giving us cash to keep us going. Thank you very much for the invite, and I'm more than happy to take any questions.
Really beautiful mechanisms there. It's really nice talk.
Thanks.
So I'm going to jump in with a question. I guess you demonstrated all of this chemistry on propionyl alcohols. So what did you demonstrate it on well, I suppose substrates without the alkynes in there? And if not, what's the importance of that? Is that
okay? So the alkynes are dictated by the Midland reduction. So the Midland reduction only works if I can go back on this. So if we look at this transition state, essentially the problem comes with these two. This isn't drawn very well. If it was drawn in a chair conformation, one of these has to be axial and one of these has to be equatorial. And essentially you have to put the propygylic group axial. And so that's why the nitriles and the propygylic groups or the alkynes work very well. And so that's really what dictates that. We could use other boranes to increase that, and other boranes have been used for more general classes of ketones, but the rates of reaction are really low. So that's something that we need to develop. One thing we would like to do is just go through a series of terpenes and see which ones we can and can't use for various things, because it's very easy to screen those now and generate those catalysts in situ and just look at the turnover.
Yeah. Cool. Yeah, it was really nice mechanism there.
It's a good group meeting problem, I think. May not be the perfect EE, but it's a nice problem for the board.
Alistair Lennox from University of Bristol. So what is the thermodynamic driving force for the transborrelation? You start with a BO and a BH bond, and you end up with the same.
Yeah, that's a brilliant question, Ali. Yeah, so it's actually the dimerization of the borane after the reaction. And this has been shown by Andrew Leach in the calculations that we did with Guy in the alkyne hydroboration paper. So it's basically thermodynamically neutral, and you can use an excess of one reagent to go either way. But the dimerization of the borane, and only the borane, drives the reaction forward, or a solvent coordination. It's the same thing. Anything that takes that borane out of solution effectively.
Cool. Nessa? I think it's probably, I'm not sure we've got that many questions coming through. So if anyone's got any questions for Iustina as well, please do type those in. Yeah, Nessa?
Yeah, is Iustina still here?
Yes, I am still here.
Still got you on the line. Hello. I thought I might switch back to a question for your talk.
Yes.
Which was here we are, from James Goldman at University of Manchester. And James is asking about the heterocycles you're using. Does it only work for nitropyridines? I think you had a quinoline as well, but are there other heterocycles it also works on?
Yes, so yes, that's true. So all we have tested were some nitrobenzenes, nitropyridines, and one example of isoquinoline. Unfortunately, we haven't tested anything else. However, when we are revisiting the project periodically for different substrates, so this could be a substrate that we have in mind. But, so far, no, just what I have shown, the nitropyridines.
Yeah, that'd be really interesting. Cool, thank you.
You're welcome.
So I'm going to jump in with another question for Stephen. So you talked a lot about the mechanism and kinetics of all of this. How, and I suppose you touched upon using Boron Nmr. Was that the only method that you used for measuring the kinetics and stuff like that? Or
we only did NMR kinetics, yeah, but not just boron. We can do proton and fluorine as well. Fluorine label one of the substrates. It's an easy way of following it around. Boron's just really good because you can see everything in the reaction. And so those is not the sharpest of NMR. It's quantitative, and you can see everything we need to see. So whether you've got 3-BBN or whether it's the alkane or the alkene that's reacting, or whatever you want to go on.
So if you try and use sort of traditional HPLC, does it just break everything down? Just
oh, you could sample reactions. That would be fine. You can't obviously expose the boronic esters to any water. They will just hydrolyze in the way you would do in a traditional middle reduction or any stoichiometric borane reduction. Okay, but you could use that. That's how we did the EE for the intermediate. We hydrolyzed it and looked what the EE was.
Okay, cool. Yeah, nice. I think we've got a couple more questions coming in for Nessa. Shall I pass over to you? We've got a couple more questions for Stephen.
Absolutely. So we've got another from Richard Horan, and he's asking about the comparison with the Cbs reduction. I was kind of wondering like how it does compare, but he's specifically asking about the mechanism.
The mechanism is very different.
Yeah. Similar but not identical was his precise words here.
So the Cbs is essentially a chiral Lewis acid.
Yeah.
This is much more like an Iori reduction almost, where you're making an oxygen metal bond, or so in our case an oxygen boron bond. So you're doing a true hydroboration rather than I know it's formal in this case, but yeah, so I can see his point, but that's much more Lewis acidic. This is not a Lewis acid driven process, and the chirality comes from the inherent structure of the borane. So in the case of the Cbs, that's BH3 rather than the oxazolidinone ligand in that case. So we're not using a ligand, we're using the actual reagent as chiral. I guess is the major difference, and Cbs is Lewis acidic. Or is it Lewis acid driven?
Okay, and we got a question from James Taylor from Bath. So can you use any alternatives to HB-PIN for the transborrelation step?
Yeah, you can. You can use whatever hydridoboronic ester, for want of a better word, where is it? I've got too many boxes on this, that you like. So if you use HB-Cat, the other commercially available one, it tends to be much faster, but there's a background reaction with HB-Cat. So you have to do that engineering solution of adding the boronic ester slowly. So yeah, you can use others, and actually we've used that in various projects as a trick to get over slow kinetics. So yeah, what I'd like to do, there's numerous ones and put all different boranes everywhere, but we haven't quite got that far yet.
Cool. So could you just switch it out for borane, or is that, I suppose that's gonna
BH3?
Yeah.
So in the case of the alkenes, you can do that very easily, because the essential alkenes are alkynes, because essentially your first reaction is the hydroboration of that 1 or 2 times to give you then the active catalyst, which is a secondary borane.
Yeah.
In the case of carbonyls, it doesn't work as well. The problem is if you can make any borohydride, you'll get racemic reduction, non-selective reduction.
Yeah. Cool.
But yeah, it doesn't have to be H9BBN. It could be dicyclohexyl, dimethyl, whatever you want to make. It's just H9BBN is commercially available.
Yeah, sure.
Okay. So are there any of these intermediates that you can see? I guess I'm kind of talking about all of these that you can see in the Boron Nmr. I mean, like this sort of
so we
weird
can see this one. We can put in we can see the catalyst, and then we can see it convert. Do you mean under catalytic conditions, or under? So in single turnover, we can see every single species along the reaction with a boron in it.
Okay, that's very nice.
In catalysis conditions, it's a bit more limited, because you're obviously only going to have 10% or 20 mol% of your catalyst instead of a maximum of 20 mol% of H9BBN. And then it has 2 peaks when it was solvated or not solvated, whether it's monomer or dimer. So it gets a bit more complex. But yeah, you can see everything and track it, so it's really nice in that way. And we can measure the thermodynamic properties, for example, of the exchange by doing the NMR work and iron plots.
Yeah, it's very cool. Maybe I should start using Boron Nmr again. I haven't used it for years on end, but I hate doing borrelations just because of the analysis at the end.
Well, if anything's close to each other, you can't see a difference, is what I should say. So,
yeah.
If you had 2 very similar structures, it would be very difficult to see between them.
So in terms of relative rates, what's is it the hydroboration that's quicker, or the transborrelation steps?
I think the transborrelation is the slowest step, because, well, I think that's the way you control the EE effectively, or the matching the EF.
Yeah.
I think essentially you lock everything up in the boronic ester and then turn it over slowly. And that's why changing from one hydride boronic ester to another gives you different rates of reaction overall, because that's how fast it can do that exchange, how Lewis acidic and how Lewis basic that intermediate is coming together.
Cool. I was thinking, I suppose you're not going to get build up of that intermediate in the middle, because I suppose it's catalytic, but
this one,
yeah. So if you don't,
yeah, so it can only be the catalyst loading.
Yeah. Okay. So if you don't do it catalytically, you just get a build up of that.
Yeah. Until you add an HP pin,
and then it just goes. Yeah. Cool.
But yeah, that's definitely the slower step there.
Cool.
Okay, so I'd like to thank again the two speakers for some really interesting ideas and some thoughts about catalysis. It's really good to see a continuing effort in catalysis from my past. I'm always susceptible to a catalytic process. But just to say, the future seminars webinars that we have in July, the next 3 are around catalysis still in some places, and so we hope everyone can attend our webinars in July. We have a full program in July right to the end. So once again, thank you to our 2 speakers. Thanks everyone for attending, and thank you all for joining the webinar today.
Thanks very much, guys. I really enjoyed that.
Yeah, thanks, guys. Really good content. Beautiful mechanisms.
Thanks, everybody.
Cheers. All right, I'll catch you again, eh? Thanks a lot.
Yeah.
Yes. Bye, everyone. Yes.
Thanks a lot.
Good talk.